Now, we want to talk about equilibrium of what? Coplanar parallel forces. This is an interesting part of equilibrium. When you understand this part very well, you'll be able to what? Solve questions, especially questions that have to do with diagram. This will enable you to do that. And I designed some methods by which you can comprehend this course effectively well. And those are the things I'm going to be applying in today's class. As you listen, God bless you. Now, equilibrium of what? Coplanar parallel forces. Why do we call it coplanar parallel force? Because the forces are what? Are parallel. This one is parallel to this and parallel to this. Now, the first thing to understand this topic, I'm going to give you some points to understand how to analyze this thing. Is number one, you must apply what they call the principle of what? Of moment. Principle of moment is a very simple principle to understand. What is this principle saying? It's just telling us that the sum of what? Clockwise what? Moment should be equal to what? Sum of anti-clockwise what? Moment, provided what the system is not under the influence of what? External force. That means there is no external constraint on the system. You know, something that is external constraint. But if there is no external constraint, the sum of clockwise moment must be equal to the sum of anti-clockwise moment. Or we can say the sum of what? M equal to what? 0. The algebraic sum of moment in a system must be equal to 0. So you can say a principle of moment states that what? In a system of parallel forces, the sum of clockwise moment must be equal to what? The sum of anti-clockwise moment. It's as simple as that. Now, what we mean by that? Before you can solve this question, or before you can apply it, you must take moment about a what? Take moment about a point. And when you are taking moment about a point, it means that you are turning that point to be what? 0. 0 moment, 0 force. So any force that is applied at that point must be turned to 0. So you render them ineffective. For example, if I take moment about this point, it means that the R1 is 0. Any other force that is acting about this point is what? 0. Just like me using knife to cut this place down. Listen, if I drop it, if I cut it down, the effect of this, this is holding it, making it to go up before. If I remove it, it will go down. This one will now move this way to balance it. This one will turn this way to balance it. So everybody will now be focusing on that. All the forces will be focusing in that particular direction. That's what they mean by taking moment about a point. Now, if I take moment about what? Let's say we take moment about what? About point what? Let's say point A. Let's call this one A. Let's call this one B. There's a normal there is a what? A knife edge there to make sure that reaction. Because without knife edge, no reaction there. Let's place a knife edge there. So we take a moment about this point. Now, if we take a moment about point A, what I want to do is that this point A, forget. This point A. Now, we now what? This one will go there. This one will come like this. This will now what? Clockwise. This is what? Anti-clockwise. So that is what is happening now. So now what? When we take moment about what? We are concerned about moment. So clockwise moment. So what we want to do now? The clockwise moment will now be force times distance to that point. Don't forget, I choose a uniform or a plank that has a length. Let me say from here to this place is L. That is the length of the plank. I use that as my length of the plank. Don't forget, I assume that is the length of the plank. And I take from here, from A to what? To the force F1 as X. If A to force F1 is X, what will now be from here to this place? L minus X, abi? Because from here to this place is L. From here to here is S. Then from here to this place will now be this minus what? This one. Now, if the moment about that point, you have what? F1 times what? X. is equal to, that is clockwise moment, because it's only one clockwise moment that we have there. And the clockwise moment is also one, which is what? R2 times what? Times L minus what? That is distance now. No, times L, sorry, times L. Because the distance from here to this place is L. Sorry for that, it's L. So this is what? You have applied moment like that. You must know how to apply moment first. That is it. You must take moment about the point. That point you are taking moment about, you are turning that point to be zero force, zero moment. So they are not going to be involved in your calculation of what? Using principle of moment. Your calculation using principle of what? Moment. Now the next thing is what? Number 2 points there is that what? The sum of forces in the system will be equal to what? So that means the algebraic sum of forces acting in the what? In the system will be equal to 0. In other words, we can say the sum of what? Of upward forces must be what? Equal to what? To the sum of what? Of downward forces of the system in equilibrium. Of a system in what? In equilibrium. Don't forget, you can also say the sum of forward forces equal to sum of backward forces along the x-axis, forward and backward. So if you check, you want to apply this one now here. How many forces are going upward? 2. R1 is up, R2 is up. So we can say R1 plus what? R2 is equal to what? How many forces is going downward? 1. So this one is upward forces. Then F what? 1. This is downward forces. So we have applied the second one. The third one is that if you have a uniform plank or a uniform meter rule, don't forget, a uniform what? Object has its what? Center of what? Of gravity at this middle. A uniform object has its center of gravity at the middle or the center. How do you know? Now, for example, if I give you a uniform meter rule, hello, once they use the word uniform, that means meter rule is what? They don't need to tell you it's for 100 centimeter. So this one will now be what? 100 what? Centimeter. So the center of gravity will be your what? At the center. This is where the CG will be. At the center. What is the center of this one? Here will not be what? 50 centimeter. While here, from here we also what? 50 centimeter. Once they mention it, and if they tell you the mass of the object, the mass of what? Of the uniform object is at the what? Is at what? The center of gravity. So if I say, for example, a uniform what? Meter what? Rule of mass 50 gram balances what? Horizontally. I want to apply what I've just talked about now. So a uniform what? Meter of mass 50 gram balances horizontally. What does that mean? Look at it. I will draw a uniform what? Meter rule. Look at the board. After drawing the uniform meter rule, I will what? This is 100 centimeter. Abi. Now, what is the midpoint of that meter rule? Here, let's say assume here. And that is where if I give you 9, what do we use to balance the meter rule horizontally? Knife edge. Knife edge or what we call pivot is what we use to balance a meter horizontally. You cannot just put a meter horizontally and suspend it in the air. It becomes spiritual. Because you cannot just balance, you have to put it on something to hold it. So if you are performing practical now, for example, you hold your metal, you hold your knife edge, put it on the table and balance it. And the balance point, if it's a uniform plank or uniform object, must be at the center of what? Gravity. That is where the balance, that is where the thing will now what? The balance. What do you mean to balance? To remain in equilibrium. What do you mean to remain in equilibrium? Not to be displaced. What does it mean to not to be displaced? To be at what? Stable. To be stable. And that is where the mass will also be at. So you would have 50 grams. So if you carry the meter, every meter will have their mass written at the back of the meter. So that is what. And that mass is always concentrated at the center. Don't forget, center of gravity is the what? Is the point where the gravitational pull of the earth tends to concentrate on. The center of gravity is the point where the gravitational pull tends to what? Concentrate on. The gravitational pull of the earth tends to concentrate. For example, what is center of gravity of a what? Of a circle at the center? What is center of gravity of a what? Of a rectangle or a square? That means the point of intersection of the what? Of the diagonal. That is center of gravity. What is center of gravity of a triangle? It's what? The center of gravity of the triangle is what? 2/3 of the height from the, if this is the height, 2/3 of the height from the apex, and what? 1/3 of the height from the base. This is the base, this is the apex, the shaft. So the center of gravity of a triangle is 1/3 of the what? Of the what? 2/3 of the height from the apex and 1/3 from the base. What is the center of gravity of a uniform plank? If this is a uniform plank of what? Of L. The center of gravity will be at the middle, at the center point. Where here will not be what? L/2, and here will not be what? L/2. And the mass of the what? The mass of the what? Of all these objects always concentrate at what? At the center of gravity. So if you are giving mass of those plane objects, it will be concentrated at the center of what? Gravity. That's how it was. The lower the center of gravity, the higher the what? The stability. Don't forget. The lower, that's why short people are always what? We say they are closer to the earth. A short person is closer to the earth. Why? Because he has low center of gravity. Fighting such a person is a loser by grappling the person, going battle to battle, a physical battle by holding the person. Because displacing the person, he will still land back on the ground. He will not fall because he's already on the ground. He cannot fall. So he has low center of gravity. But somebody that is tall can easily be pulled away from the ground because he has high center of gravity. You have seen a case of a slim girl that will be walking as if he's doing, demonstrating. He's trying to show people that he's beautiful, but he's controlled under gravity. He's being moved by gravity. He's all those. So it's very interesting topic anyway. We shall still go to talk about it under equilibrium, types of equilibrium. But nevertheless, let us face what we are doing. Now, this body now, it balances at the middle, knowing fully well that no object is added to it now. We did not add any mass to it. Now, just like what we call Lechatilia's principle in chemistry. Now, if you add a mass, the system will not be balanced again. So you have to move the pivot in a way that to annul the effect that the external mass or weight have been added to the system. For example, if I add a mass here, for example, if I put a mass of what? Of let's say 10 grams here, this body will not be balanced here again. Because there will not be what? Displacement in this direction. Because there is now more moment on this side than this side. Don't forget there are two sides of it now. There's one side here, there's one side. This one is not carrying any load here. This one is carrying load. So this side what? We drop down. Why this one what? Want to cause a turn. Don't forget, moment causes a turning effect. You understand? We want to turn. Now, how do I, because we don't want turning here, we want equilibrium for crying out loud. So what do we do to cancel that rubbish that is trying to happen there. It's just a what? Move the what? The pivot closer to the what? To the force. So that to annul and to cancel. If you move it further, it will even displace it more. So you move it closer to the mass. Yeah, it will not be. We will know that time when we want to solve question. But if I move this mass to this side, what happened to the pivot? Well, as the pivot is moving, will the mass of the meter will move? No. The mass of the meter will remains at that point or at that center. It remains at that what? At that center. It will not move at all. Because why? It is part of the body. It is mass, is the quantity of matter of the body, of the plant, of the metal. It cannot move. It does not change. It cannot change position there. It will remain there. What will move is what? Your pivot. Because that's what is balancing it. So if I move this one now to the right, the pivot will move to the right. So note this. When an external weight is added to the right, the pivot moves to the right in order to annul the what? The effect of the external load added to it. When the load moves to the left, the what? The pivot will also adjust to the left to annul the effect of that what? External load added to the left in order to keep the system in what? Equilibrium. Because if equilibrium is not achieved, there is a problem. What are the problems? You cannot apply this principle. Number two, you cannot apply the what? Principle. So these two principles are only valid for what? For equilibrium system. They are only valid for what? Equilibrium system. Please don't forget that. And anytime you have a knife edge in a what? In a system, it produces a reaction, an upward force. A knife edge will produce a what? A reaction. When a load is added to the system, it produces a downward force. A load, when like this one is a load, the force will be acting downward. It's not possible for the force to be acting upward. Just like the way my students are sitting down now, their weight cannot be acting upward. Somebody is sitting down, the weight is happening downward. It's not normal now. It's not physics any longer. Because the weight is always acting in the direction of what? Of gravity. So what we have discussed now so far, it has explained everything about how question can be solved on equilibrium. Now, what I want to do lastly is to talk about what we want to clean the board now, to talk about what we call types of what? Equilibrium. We have different types of equilibrium. We have what they call the stable equilibrium. We have the word unstable equilibrium, and we have what? The neutral equilibrium. Stable equilibrium is when the body is displaced, it tends to return to its original position. That's what we call stable, to be stable. Then unstable, when the body is displaced, it does not return back to what? Original position. But neutral equilibrium, it tends to, when it's displaced, it goes to a new what? Position. It goes to a new position. So that is what they call stable, unstable, and neutral. So that is the last one I want to talk about. Now, we stop at what? Stable, unstable, and neutral. The question is, what is stable, what is unstable, and what is neutral? Now, stable equilibrium is what? Is what? When a body is what? Or a body, let me put it what? A body displaced, and it returns to what? To its what? Original what? Positions. So it is what? A stable equilibrium can be achieved, or is when a body is displaced, it what? It returns to its what? Original what? Position. Now, what are the examples of a stable equilibrium? So when we talk about stable equilibrium, what do we mean by that? Number one, what are the things to watch out? It must have a wide base. Wide base. Number two, it has what? Low what? Center of gravity. Low center of what? Gravity. Low center of gravity. For example, if I draw something like this here, look at it. This is what? A stable equilibrium. For example, if I draw another one here, this is unstable. Let me draw another one here. Now, this one now resting on it, what? That widest part of it. This is what? Neutral. I can have another one like this. This is stable. This is unstable. And this is neutral. Neutral, the body always starts with what? It what? Edge slant what? Height. Is resting with this slant height. That is neutral. We can have a stable like this. These are common questions I'm using as example. We can have unstable like this. And we can have a neutral like this. Neutral equilibrium. So I can continue. We can use stable like this. Stable. We can draw unstable like this. And we can draw neutral like this. So these are possible examples of what? Stable, unstable, and neutral. I will explain it. Now, for stable equilibrium, it must have what? A minimum potential energy. Why? Potential in the sense that look at their center of gravity here. This center of gravity. When the center of gravity, somebody that is closer to the earth self, they say what? They have a low center of gravity. The height of that person is small now. So when you are calculating potential self of that person is small. But somebody that is tall has the higher what? Potential energy because the height of that person. So it's open to what? Displacement. It's open to displacement. If I tilt it, it will what? It will become a very unstable object. Probably what will not return back to that point. If I tilt, imagine when you are tilting, you tilt slightly. When you are displacing, you displace slightly, not that you just push anyhow. Now, if I displace this one slightly, maybe displace like this, it will fall. But if I display this one a little, maybe raise it up, it can return back to the original. If I display this one, it can move and change position. We check. The base of this one is wider compared to this one. This one is narrow. So if I say unstable has a narrow base, the base we are talking about is this side. And look at the center of gravity of this side. As a high what? Center of gravity. Look at where it is. The center of gravity is high. So since it has high center of gravity, it has what? High what? Center of what? Of gravity. Then it has what? A maximum what? Potential what? Energy. But you can increase it to, how do you increase? Don't forget, if I raise this, if I tilt the object upward, I will increase what? The maximum what? That means if I tilt it by displacing it, you will now discover that they will now have a maximum what? Potential energy, because they will now come back to position. I hope you know. Yes. What is potential energy? Potential energy is what? The ability of a what? Of a body to remain in what? In position. You understand? So this thing what you increase your potential energy during displacement. So that, and when you increase your potential energy, they become stable because of what? When they are increased, they become stable. And when they become stable, they have what they call maximum what? Kinetic energy. No, kinetic energy is what? Is higher at the what? At the closer to the earth. I mean, potential is what? Higher away from the earth. When you throw a body upward, it tells you when it's about to hit the ground, the velocity is maximum. And velocity is a function of what? Kinetic energy, which is mc squared. So it's 10 to magnitude. But potential energy is maximum at the highest point. So this one is what? What is the center of kinetic energy? It has a minimum what? But when you displace them, have what? Maximum kinetic energy. When you displace them, they have what? Because they will now what? When you displace them, they will not return to you what? To that position again. And you understand now? So that means that they will have reduced what? The potential energy and increase what? Kinetic energy. So in this case now they have maximum what? Potential energy. But what about neutral? Neutral what? Equilibrium is everything is neutral. It's because it's neutral. For potential energy is unchanged. Kinetic energy, these are neutral equilibrium. All this one like this, they are neutral. All this one are stable. This one like this. So this is A is stable, example. B is unstable, example, and C are example of what? Of neutral. So you can use them for what? When this one, when they are displaced, they take a new what? Position. So So you see now, I just gave you a summary of that. When displaced, it returns to a new what? Position. That means if I give you this ball now, for example, if this ball move from here to this, if I displace it, get to this point, as the center of gravity change, hello, look at it. As the center of gravity change, no, it does not change. From here, it still retain here. You only move from one point to So that ends the topic for what? Equilibrium and moment. I think you enjoyed the class, so you can subscribe. And if you are just watching my video for the first time, and if you are a returning viewer, thank you for watching. God bless you. Have a wonderful day. Thank you.